Next topic, binary codes. Code is nothing but what? Group of some symbols. Here we are using the term binary. That means we are using the symbols 0 and 1. Okay. So that means binary code is nothing but group of symbols or pattern of symbols. Here in this case we will represent in terms of zeros and ones. Okay. So we can classify the binary codes into two categories. Here we can classify the binary codes into two categories. One is alphanumeric, another one is numeric codes. Just leave some space here. I will give some points. Okay, you can note down. See here, if you observe, you are having two wordings. One is alpha, another one is numeric. That means what? This particular code we will use for representing both alphabets and numbers. Okay, you can write down. Just leave some space for the classification. You can write down after leaving some space. A binary code is said to be alphanumeric code if it can be used for representing both alphabets and numbers. That means if a binary code we are using for representing both alphabets and numbers, then we will call it as alphanumeric codes. Whether hexadecimal number system belong to alphanumeric code or not. Because see here, just go through the sentence, whatever I have given. Here the binary code I am using for representing both alphabets and numbers. But actually, see what is the code for your hexadecimal code for letter Z? We don't have. Right? See actually what there we are using, see the pattern, say 10102 all ones, the equivalent value 10 to 15 we are getting. We cannot represent 10 to 15 with the single digit. That's why I am using alphabets, say A to F, I am using for representing my equivalent value. But I am not using the code for representing the alphabets. See, I don't have any code for letter Z in hexadecimal, right? So here example is ASCII code, right? In the keyboard you are having both alphabets and numbers, right? So there you are having 7-bit code. See, whenever you are pressing any key, internally the equivalent 7-bit number will be generated. Okay. So there we are representing in terms of zeros and ones. Okay. We are having one particular code. That particular code we are using for representing both alphabets and numbers. Numeric code means if a particular binary code we are using for representing only for the numbers. If we are using the code for representing both alphabets and numbers, then it is alphanumeric. Okay, next point. If a binary code is used for representing the numbers, then it is said to be numeric code. Okay, we can classify numeric codes into two categories. One is weighted codes, another one is non-weighted codes or unweighted codes. We can classify the numeric codes into two categories. One is weighted, another one is non-weighted. Here weighted means what? Positional weights. Here we will be having positional weights. Okay. But whereas non-weighted code or unweighted code, that means here we don't have any positional weight. Okay. Next point. A numeric code is said to be weighted code if it is having positional weights. Regarding weighted code, example is 8421 code or BCD code. Regarding unweighted codes, you can write down one statement. A numeric code is said to be unweighted code if it is not having any positional weights. What are the examples for unweighted codes? XS3 code and Gray code. These two codes are not having any positional weights. So that's why these are the examples for non-weighted code or unweighted code. Now let us discuss these three codes. Okay, as per gate exam point of view, we will focus on the numeric codes. Okay, first one, put the heading 8421 code. 8421 code or BCD code. You can write down binary coded decimal. BCD means binary coded decimal. Alphanumeric code means what? You are having the binary code that can be used for representing both alphabets and numbers. Okay, whatever the keys you are pressing from the keyboard, you are having both alphabets and numbers. Internally, there will be a 7-bit code corresponding to each alphabet and number. Okay. So that means you are having group of zeros and ones or bits or group or symbols of pattern of zeros and ones, right? So that particular code you are using for representing alphabets and numbers. You are having capital letters, small letters and then numbers. Okay. That is related to ASCII code. Whatever the 7-bit code you are having, that 7-bit code is nothing but ASCII. So ASCII is the example for alphanumeric code. There we are using combination of zeros and ones for representing both alphabets and numbers. Whereas numeric codes, we are using the code. That means in terms of zeros and ones we are using for representing the numbers. That is the difference between alphanumeric and numeric. Okay. Here first we are discussing about 8421 code. Here BCD is nothing but binary coded decimal. Okay. That means we are using binary format only. See, if you observe here, position weights 2 power 0 is nothing but 1, 2 power 1 is nothing but 2, 2 square is nothing but 4, 2 cube is nothing but 8. That means we are having the position weights in the like binary 2 power 0, 2 power 1, 2 square, 2 cube. But we are using these particular symbols of zeros and ones for representing decimals. That's why here 8421 code is called as BCD, binary coded decimal. Here we are having 10 decimal digits, 0 to 9. Okay. Now we are representing these numbers in terms of zeros and ones. Okay. You are already familiar for these numbers. Okay. You can directly write the equivalent values. Or whenever you want to write the corresponding pattern of zeros and ones, just observe by adding which position weights you are getting the equivalent value. So under those position weights you have to place the 1. So here first case 0 is the equivalent value, that means all the bits should be zeros. Next, second one is 1, that means under the position weight 1 I am placing 1. So that equivalent value is 1, remaining bits are zeros. Similarly here 2 is nothing but bit value is 1 under this position weight, remaining bits are zeros. Next 3 is nothing but 2 plus 1, so I will place 2 ones here. Next 4 is nothing but here 1, remaining bits are zeros. Like that, by adding which position weights we are getting the equivalent value, you can place the ones under those position weights. 5 is nothing but 0, 1, 0, 1. 6 is nothing but 4 plus 2. 7 is nothing but 4 plus 2 plus 1. 8 is nothing but 1, 0, 0. 9 is nothing but 8 plus 1. Okay, so that means, see here we are having only 10 decimal digits, 0 to 9. Okay, for representing these 10 digits, we are using the binary code 2 power 0, 2 power 1, 2 square, 2 cube. But actually, if you observe, here I am having 4 bits. Okay, if you are having 4 bits total, you can have 16 combinations. But since we are having only 10 decimal digits, we are using 10 combinations of zeros and ones, right? So what about the remaining 6 combinations? Say 10102, 1010, 1011, 1100. These 6 combinations are not valid BCD code. See, whatever the code here we are having 0 to 9, all these are valid BCD code because we are using the binary code for representing the decimal digits. Okay, for representing 9 I require 4 bits, right? Maximum decimal value you can represent for a single digit is 9. For represent 9 I require 4 bits. That means with the help of 4 bits you can represent all the remaining digits. For a single digit, whatever the remaining values you are having, all those values you can represent with the same 4 bits. But since you are having 4 bits total, you will get 16 combinations of zeros and ones. But among which only these 10 combinations are valid BCD. These 6 combinations are non-valid BCD. Non-valid BCD codes. See, in the binary, these numbers will exist. But for this code, binary coded decimal, these are not valid. These are not valid. Okay. Say 10102, 4 ones, these are not valid BCD codes. Suppose if you want to represent 10 in BCD code, we can represent like this. 10 is the decimal number. I want to represent 10 in the BCD code. See here how many digits you are having? 2 digits, right? So for each digit I will use 4 bits. See, 1 is nothing but what? 0001. Okay. 0 is nothing but 4 zeros. So this is the BCD code. So in this case, after placing the equivalent value, see here 1 is nothing but 0001, 0 is nothing but 4 zeros. So in this case, if you observe to the left of this particular 1, you are having 3 zeros. Okay, in this case, I won't remove these 3 zeros because of insignificant. Okay, whenever we have done hexadecimal to binary conversion, there on the leftmost side, okay, if we are getting zeros, I can remove because there I have mentioned those zeros are insignificant. But whereas in BCD code, for representing each decimal digit, we require 4 bits. Okay, so in this case, we should not remove these 3 zeros. Okay, see if you are having the code like this in terms of zeros and ones, by doing the grouping of 4 bits, okay, you will get the corresponding decimal digit. 4 zeros is nothing but 0. Similarly, 0001 is nothing but 1. So that means what? For representing each decimal digit, we require 4 bits in the BCD. Okay, you can write down. For representing each decimal digit, we require 4 bits in the BCD code. Okay, so you can make a note. If there are k decimal digits, see, for each decimal digit, we require 4 bits in the BCD. Suppose if you are having a decimal number having k decimal digits. Okay, if the decimal number is having k digits. Okay, if the number or if the decimal number is having k digits. Okay, then the number of bits required in BCD code is how much? For single digit, I require 4 bits. Okay, I am having k digits. Yeah, 4k, right. For each decimal digit, we require 4 bits. Here I have considered k decimal digits. So that means we require 4k bits. See, the purpose of BCD code is whenever some users or programmers want to perform the operations, okay, whatever the resultant value they are getting from the computer, okay, if they wanted to represent that particular number in the corresponding decimal, okay, so if you are having the binary format, there you have to convert, okay, if you are having more number of bits, just by looking at that particular number, you cannot say what is the equivalent decimal number, right? So, but here, if you are using, say, BCD code, here the advantage is just by doing the grouping of 4 bits, you will get the corresponding decimal digits. See, we are familiar for 4-bit case. Just by looking at the 4-bit number, we can write what is the corresponding equivalent value. So that means this is the advantage. Whenever you are supposed to perform or represent the whatever the number you are getting, that number into decimal, if that frequency is more, okay, so there you can represent the binary number in BCD code. Okay, so that what will happen? If you do the grouping of 4 bits, just by looking at the 4 bits, you can directly write the corresponding decimal digits. So that is the advantage of BCD code. But the drawback is we require more number of bits when compared to binary. Yeah, the drawback is there. But the advantage is just by looking at the 4 bits, we can write the corresponding decimal digits. In binary, if you are doing the grouping of 4 bits, then you will get hexadecimal digits. From that you will get the equivalent value. From that you have to convert into decimal. So much process there. But here, just by looking at the 4 bits, you will get the corresponding decimal digits. Yeah, same thing applicable for fraction also. Here we are representing individually each decimal digit with the 4 bits. Write down the question. Represent the decimal number 43 in hexadecimal and BCD number systems. See, first let us convert this decimal number into hexadecimal. Do repetitive division with 16 in order to get the remainders. Remainders will be of what? Hexadecimal digits. Okay, hexadecimal number system. 2 16s are 32. Remainder is 11. 11 is nothing but B. 16 zeros. Remainder is 2. So that means 43 decimal number is nothing but hexadecimal number is 2B. That is the first part. Another part is this is the decimal number 43. We have to represent in BCD. That means for each decimal digit we require 4 bits. 4 is nothing but 0100. Then 3 is nothing but 0011. This is the BCD code. For this question, answer is hexadecimal format 2B is the answer. In BCD format, this is the answer. Okay. Now, just let us convert this hexadecimal number into binary. That means each digit we have to represent with 4 bits, right? So 2 is nothing but 0010. Next, B is nothing but 1011. This is the binary number. Okay. Now, see, whenever we have converted from hexadecimal to binary, here I got, suppose, leftmost side zeros. So these zeros are insignificant. So I can remove these 2 zeros. So the answer is 101011. So that means for representing the decimal number 43 in binary, I require only 6 bits. Whereas for representing the decimal number 43, I require 8 bits in the BCD. But just by looking at this binary number, we cannot write the corresponding decimal number, right? It will take some time. But the advantage of BCD code, here we are representing with 4 bits. Just by doing the grouping of 4 bits, we will get the corresponding decimal. That is the advantage. Here, actually the main advantage of binary is we require less number of bits. Okay, but the drawback is just by looking at the grouping of 4 bits, we will get the hexadecimal digits. From that, in order to get the decimal, we have to put the position bits and then we have to find out the equivalent value. But whereas if we are representing the number, okay, in BCD format, that means by doing the grouping of 4 bits, we will get the corresponding decimal digits. Next one, put the heading XS3 code. XS3, as the name implies, 3 already has been included. That's why here the wording is XS3 code. That means just by adding 3 to the BCD code or 8421 code, we are getting the code corresponding to the decimal digits. Here we have represented 8421 code for representing decimal digits. Okay. Here also XS3 code, we are representing the code for decimal digits only. But here 3 has been included. That means suppose for 0 we are having 4 zeros. Okay, if you add 3 to it, you will get 0011. That means 0011 will be the representation of 0 in XS3. That is the meaning. You can write down XS3 code is nothing but BCD code or 8421. Anything is okay. BCD code plus 3. Or you can write 8421 code plus 3, you can write it as 0011. Here I am having 4 bits. Okay, just add 0011. You will get the code corresponding to the same decimal digit. 0 is nothing but what? Here you are having BCD code as 4 zeros. Add 3 to it, you will get 0011. That means 0011 is the code, XS3 code representing for decimal digit 0. Like that, just add 3 so that what you will get here for 0 you will get 0011. For 1 you will get 0100. Like that, here for 9 plus 3, that means 12. Nothing but 1100. Okay, like that, complete the tabular form. Just add 3 to it. Okay. Just add 3 to it and represent in binary. Simple. 2 plus 3 is 5. 5 is nothing but 0101. 3 plus 3 is 6. 6 is nothing but 0110. Like that. So here we are having 3 to 12. Right? For 0, this is the representation in XS3. For 9, 9 plus 3 is 12. So that means what? Forward direction, whatever the code we are having in BCD, we have added 3 to it. So that we are getting the code. Okay, in that code, where already 3 has been added, that's why this particular code is XS3. Okay, reverse way. Suppose if you are having this particular code, okay, he will mention, what? See here, everything we will represent in terms of zeros and ones only. But based upon our interpretation or based upon the question, he will mention, if so and so binary number is represented in XS3, suppose example. Okay, so based upon that, the equivalent value will change. If you are considering unsigned category, equivalent value is another one. If you are considering suppose 1's complement or 2's complement, like that, he will mention whatever the binary number is there, that particular number is belong to so and so. He will specify. So accordingly, you will get the equivalent value, right? So that means, see here, if you are having the combination like this, 0011, okay, just by looking at this one, okay, he will mention this particular code is available in XS3. Now, in order to write the equivalent decimal value, you have to separate 3 from it. See, in the forward direction, we have added 3 to it. We got the code corresponding like this. Okay, 0 is nothing but 0 plus 3 is 0011. 9 plus 3 is 12. That is nothing but 1100. In the reverse way, if you are having the code this one, okay, we want to represent the corresponding decimal digit. So we have to separate 3 from it. 3 minus 3 is 0. 4 minus 3 is 1. Like that. 12 minus 3 is 9. Okay. In binary, we have discussed 2 types of complement. One is 1's complement, another one is 2's complement. Why we are going for 2's complement? Whenever we are supposed to perform subtraction, right? So instead of doing separate subtraction, right, we are representing that negative number with the help of what? 2's complement of positive number. So that we are adding those 2 numbers, right? So similarly, in the decimal number system, we will be having 10's complement, 9's complement. In the similar way, octal number system, 7's complement, 8 complement. In hexadecimal, 15th complement and 16th complement, like that. So whenever we wanted to do subtraction, there you can use the complements. That is the advantage of complement technique. So in the decimal number system, you will be having 9's complement and 10's complement, right? Suppose here, I am considering, suppose number, say 4. I am considering one digit, that value is 4, decimal digit. I want to perform 9's complement of 4. 9's complement of 4. Actually, the meaning of 9's complement or 1's complement or 2's complement, see, let us see. Suppose if you wanted to find out 1's complement, I am having 1 bit. For the time being, I am considering single bit. Okay. I want to perform 1's complement of single bit. Okay. See, if you are having the single bit, you can represent either 0 or 1. Only two combinations. Either you can represent 0 or 1. Right. So the maximum value you can represent for a single bit is 1. Right. So 1's complement of it means you have to subtract that particular number. That is the meaning of actual meaning of 1's complement. I am having suppose bit 0. I want to perform 1's complement. The meaning is you have to subtract the 0 from 1. Similarly, if you are having bit value 1, 1's complement of 1 means you have to subtract this bit from 1. That means actually you have to perform like this. Okay. So here what is happening? 1 minus 0 is nothing but 1. 1 minus 1 is nothing but 0. Just by observe, here we are performing 1's complement of 0. That means 0 is changing to 1. Similarly, 1's complement of 1. 1 is changing to 0. That means what? Instead of performing subtraction, directly what we are saying, here if you are having bit value 0, it is complementing to 1. Similarly, if you are having bit value is 1, complementing to 0. Like that, we are directly saying. Okay, but actual internal phenomena is what? Like this. If you are having the single bit, if you wanted to perform 1's complement, you have to subtract that particular bit from 1. And then 2's complement means whatever the 1's complement value you got, add 1 to it. Like that, similarly in the decimal number system, if you are having the decimal digits, okay. So if you are supposed to perform 9's complement, then you have to subtract that particular digit from 9, like that. Okay. So here 9's complement of 4 means actually you have to perform 9 minus 4. 9 minus 4 is how much? 9 minus 4. 9's complement of 4 means you have to subtract this particular digit from 9. That is the meaning. 9 minus 4 is 5, right? Now, actually we have to perform this particular operation. I am considering one decimal digit 4. I want to perform 9's complement of it. Actually what I have to do? I have to subtract that particular 4 from 9. So 9 minus 4 is 5. Now, let us consider the code corresponding to 4. The code corresponding to 4 is what? 0 triple 1. 0 triple 1. Now, just do 1's complement here. What will happen? I am considering this code. Apply 1's complement. What you will get? Now look at this particular table. Regarding 1,000,000, what is the decimal equivalent you are having? Just look at this table. Regarding 1,000,000, what is the decimal equivalent you are having? Yes, 5. 5 is nothing but 1,000,000. So that means here what is happening? Actually we have to perform subtraction, but the advantage of this XS3 code is, okay, whatever the decimal digit you are supposed to perform 9's complement, the code corresponding to it we will consider and we will apply 1's complement to it. 1's complement is very simple. What you have to do, if 0 is there, that will become 1. If 1 is there, that will become 0. That means with the help of inverters, we will complement the bits. Okay. So directly you will get the resultant value. Okay, that is the beauty of XS3. See, this particular technique is not there in the BCD code. That's why we are going for XS3 code. See, earlier when they wanted to perform the arithmetic operations like addition and subtraction, especially for subtraction, they will use XS3 code. Here, whenever they wanted to perform 9's complement for representing the negative numbers, okay, there, whatever the code you are having the corresponding decimal digit, apply 1's complement to it, you will get the corresponding code. So that will be the resultant answer. Just observe here, for 0 you are having this one. 9's complement of 0 means 9 minus 0. That is nothing but 9. Right? Complement all these bits, 1100. Similarly, for 1 you are having code this one. 9's complement of 1 is 9 minus 1, 8. Complement here 1011. Okay, like that similarly it will applicable. Check for remaining. Similarly, if you consider 9, 9 is nothing but 1100. 9's complement of 9 means 0. That means here you are supposed to get 0. How I am getting? Just by complementing these bits 0011. Okay, you can write down this particular property is self-complementary code. You can write down, put the heading self-complementary code. Self-complementary code. Put the side heading self-complementary code. If 9's complement of a decimal digit is equal to 1's complement of the code corresponding to it. Okay, you can write down example for one case. 9's complement of 4 means 9 minus 4. That is nothing but 5. Here I have taken the code for 1, code for 4. I have applied 1's complement. I am getting the code corresponding to 5. Okay, you can write down XS3 code is the example for self-complementary code. Example for self-complementary code is XS3 code. So write down the question. the state of a 12-bit register is. He has given the 12-bit register data like this. The state of a 12-bit register is 1000, 1001, 0111. Full stop. What is its content? CONTENT. If it represents case 1, 3 decimal digits in BCD. Case 2, 3 decimal digits in XS3. 3 decimal digits in XS3. Case 3, a binary number. See here, he has represented in terms of ones and zeros like this. Okay. So, and he has given the related to this particular code or information. Here he has specified in 3 cases. If this particular code is representing 3 decimal digits in BCD, then what is the equivalent value? If it is representing 3 decimal digits in XS3, what is the equivalent value? If you are treating this is the binary number, what is the equivalent value? Like that. That's why I have mentioned. Here everything we will represent in terms of zeros and ones only, but based upon our interpretation or user interpretation, okay, the equivalent value will change, right? In the case 1, here he has mentioned 3 decimal digits in BCD. That means whenever you do the group of 4 bits, you will get 1 decimal digit. Here you are having 3 such groupings. That means you will get 3 decimal digits. Okay. In case 1, if you are treating whatever the group of 4 bits you are having, okay, that group, if you are considering BCD, what is the equivalent value? Like that. Case 2 is, if you are treating that one is XS3, what is the equivalent value? Like that. Okay. So here, now I have done grouping of 4 bits. Okay. First consider it is the BCD. Then what you will get? 0111 is nothing but 7. Okay. 1001 is 9. 1000 is 8. Just go through the tabular form. This is the answer. Decimal number 897, provided this code is available in BCD, like that. Whenever you are doing the grouping of 4 bits, you will get the corresponding decimal digits. Okay. Similarly here this particular code is available in XS3. That means already 3 has been added. Okay. If you want to write the corresponding decimal digits, what you have to do? Subtract 3 from each digit. 7 minus 3 is 4. 9 minus 3 is 6. 8 minus 3 is 5. If you go forward direction, I am having the decimal digit 5. I want to represent in XS3. 5 plus 3 is 8. This one is 1000. Then 6 plus 3 is 9. 9 is nothing but 1001. Similarly, 4 plus 3 is 7. 7 is nothing but 0111. Like that. Okay. Forward direction, we are adding 3. Backward direction, we have to subtract 3 from the corresponding decimal digits. Okay. Previously, I have assumed this is the BCD code. Okay. So, I got the decimal digits here. So, you have to subtract 3 from each. Next. If you are considering this is the binary number, then whenever you are doing grouping of 4 bits, you will get hexadecimal digits. Isn't it? So, that means here, whatever the number he has given, if it is a binary, okay, by doing the grouping of 4 bits, here I got 897. That same 897 you will get, but if you are treating this is a binary number means what? 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, like that it will go. That means whenever you are doing the grouping of 4 bits, then you will get the hexadecimal digits. That means base is 16. Now you write position weight 16 power 0, 16 power 1, 16 square. Multiply each digit with the respective position weight and add. You will get the equivalent value. How much you are getting? This one? Yeah, 2199. Correct. Now just observe, for the decimal number 2199, I am having the equivalent binary number like this. Okay. But just by looking at these bits, I cannot directly write the corresponding equivalent value. Okay, that is a drawback. Okay. But here, I have represented this particular in terms of zeros and ones. If we are considering this is a BCD code, then by doing the grouping of 4 bits, we can directly get the decimal digits. That is the advantage of BCD code. Sequential code. If the difference between successive codes is equal to 1, then that binary code is said to be sequential code. Suppose for example, in 8421 code, for decimal digit 4 we are having 0100. Okay. For the next number, successive number 5, we are having the code 0101. Just observe, for 4 we are having the code 0100, for 5 we are having 0101. Okay. The difference between these two, that means subtract smaller from larger, you will get the difference as 1. if the difference between successive digits, whatever the code we are considering, if the difference between successive digits is equal to 1, then we can call that particular binary code as sequential code. Okay, so you can write down examples as 8421 and XS3 code. Here 8421 code we have represented for decimal digits. Okay, if you consider any two successive codes, the difference will be 1. Similarly in XS3 code also. XS3 code we have represented for decimal digits. You can consider any two successive codes, the difference will be 1. If you are having difference is 1, then we can call that particular binary code as sequential code. Next one is unit distance code. You can write down regarding unit distance code. A code is said to be unit distance code if the number of positions differed by 1 bit. A code is said to be unit distance code if the number of bit positions differed by 1 bit. See here in the sequential code, the difference between successive codes is equal to 1. But here we will arrange the code in such a way that if you consider any two successive digits corresponding code, only 1 bit position only will differ. Okay, so example is gray code. See here in the sequential code, suppose for 4-bit case I am considering. Okay, if you are having 4 bits, you will be having total 16 combinations. Okay, so for the time being, I am representing the number 7. In binary, how will you represent? 0 triple 1. You can represent as 1 triple 0. See, whenever the lift is going from one floor to another floor, okay, suppose wherever the lift is in a particular floor, the corresponding number will be displayed as 7 segment display, right? Suppose if the lift is in 7th floor, okay, so there it will display as 7, okay, the corresponding code is 0 triple 1 if I am considering as a binary, okay. Then the lift move to say 8th floor, then it will display as 8, okay. So here internal code is what? 1 triple 0. Here if you observe, even though the 7 and 8 are successive digits, okay, but internally what is happening? This bit has to change to 0, all these bits. Here 1 has to become 0, 1 has to become 0, 1 has to become 0, 0 has to become 1. So here what is happening? Even though these two are successive digits, okay, in our decimal, but internally the code corresponding to it, if we are considering the code corresponding to those digits as binary, then what is happening? All the bits have to be changed. Okay, if we are having more number of bits, okay, there what will happen? In a practical situation, okay, if all the bits have to be complemented, okay, due to some reason if any bit doesn't complemented, or if it is taking little more time in order to get complemented, then you will get the code corresponding to some other number, right? So here in this case 0 triple 1, if all the bits have complemented, then you will get 1 triple 0, then the corresponding decimal number is 8. Okay, instead of this, if any one of the bit has not complemented, then you will get some other number, it will display as some other number, right? So that is a drawback of sequential code. Drawback of sequential code is if you are having more number of bits, okay, if all the bits have to be complemented, okay, then if due to any reason, if any bit doesn't complement it, then you will get the code corresponding to some other number. That means you will get the false results or wrong results, right? So that's why we are going for unit distance code. Here we will arrange the code in such a way that only 1 bit position only will differ. You can consider any two successive codes, only 1 bit position only will differ. See, instead of complementing all the bits, right, sometime, for each and every case, if it is to be complemented only one particular bit, that is easy, right? So that is the advantage of unit distance code. Here only 1 bit position only will differ. And the example is gray code. Now let us see the gray code. First you can write down 4-bit binary code. Here we have considered 4-bit binary code. Okay. And let us write the corresponding gray code for 4-bit. Sequential code and unit distance code are not same. Okay. Here we'll see. After forming the tabular form, you will get the clear understanding. Okay, here I am considering 4 bits. So total you will be having 16 combinations of zeros and ones. First let us write all those 16 combinations. Here I have considered 4-bit binary code. Since I am having 4 bits, I have represented all the 16 combinations of zeros and ones. Okay, now let us write the gray code corresponding to each one. Here what we will do, whatever the MSB bit you are having, okay, that MSB bit we will copy as it is for each and every code. Okay, so here MSB is 0, I am copying that bit as it is. Now I will write the gray code like this. See, just observe two bits, successive bits. Okay, if there is a change, then we will write output as 1. If there is no change, output as 0, like that. Here I have copied MSB bit as it is. Okay, and then I am checking two bits, 0 0, no change, so output is 0. Next, 0 0, no change, output is 0. 0 0, no change, output is 0. Okay, for all the cases, we'll copy the MSB as it is. Here MSB is 0, I have copied. Here 0 0, no change. If no change, output is 0. 0 0, no change, output is 0. 0 1, change is there. 0 to 1, right? So whenever change is there, output is 1. If there is no change, output is 0, like that. Here MSB bit is 0. Now check two bits. 0 0, no change. 0 1, change is there, right? So output is 1. 1 to 0, change is there. If there is a change, output is 1, like that. Here MSB is 0. Then check two bits, no change. 0 1, change is there. 1 1, no change, output is 0. For all the codes, first copy the MSB bit as it is and then check two bits. If there is a change, output is 1. If there is no change, output is 0. So in this way, complete the tabular form. Yeah, I am repeating once again. See, first we will copy the MSB bit as it is. Okay, here MSB bit is 0, I have copied. And then I will check two bits. See, 0 0, no change. No change means output is 0. Here 0 0, no change, output is 0. 0 0, no change, output is 0. Next, MSB bit is 0, I have copied. 0 0, no change, output is 0. 0 0, no change, output is 0. 0 1, change is there. 0 to 1, right? Change is there. That means output is 1. Next, MSB bit 0 copied. 0 0, no change. 0 to 1, change is there, right? So output is 1. 1 to 0, change is there. So output is 1. Next, 0, MSB I have copied. Then 0 0, no change. 0 1, change is there. So output is 1. Next, 1 to 1, no change. Output is 0. Whenever there is a change, output is 1. If there is no change, output is 0, like that. Okay, in this way you can complete the tabular form. See here, if you observe, you will get the tabular form like this. Just cross check once. Here, just observe. This is the sequential code. Sequential code means whatever the decimal numbers you are having. Okay, regarding that we have represented in terms of zeros and ones. See here, 4 zeros is nothing but 0, 4 ones is nothing but 15. This is the binary number or binary code. Okay, here whatever the decimal equivalent if you are writing 0, 1, 2, 3 up to 15. Okay, so corresponding those digits we have the code like this. Okay, this particular code is called sequential because if you consider any two successive codes, the difference will be 1. Now let us observe this particular gray code. Just observe, here all the bits are zeros. Here only this bit is changing, 0 to 1. Right, remaining 3 bits are same. Next, here only this bit is changing, remaining bits are same. Next, this bit is changing. Like that, you just observe this particular tabular form. Okay, you can consider any two successive codes. Only one bit only will change. Remaining bits will be unchanged, like that. Okay, so here for 4-bit case, okay, just observe, I am considering this is for gray code for 2-bit case. Gray code for 2-bit case. 0 0, 0 1, 1 1, 1 0. Only 1 bit position only changing. Okay, so this is the gray code for 2-bit case. Okay, so whatever the gray code you got for 4-bit case, whether it is correct or not, you can just cross check like this. Okay, I have considered the gray code for 2-bit case like this, 0 0, 0 1, 1 1, 1 0. Okay, now I have to formulate the gray code for 4-bit case. Okay, so that means you will be having total 16 combinations, right? So first I am considering 0 0 for 4 combinations. 4 combinations I have kept MSB bits as zeros. Okay, remaining bits as like this. Next, second one is what? 0 1. 0 1 for 4 more times. Next, after that 1 1 for 4 times and then 1 0 for 4 times, like that. 0 0 4 times, 0 1 4 times, 1 1 4 times and then 1 0. Next, here I have placed the gray code like this. Now I am drawing the mirror image. Suppose if you put mirror here, for least significant bits I am talking about. Okay, the mirror image like this. Here if you put mirror, this one will reflect here, right? Similarly here, 1 1 will reflect, then 0 1, then 0 0. Okay, after that, whatever I am having, I will copy as it is. Now you can see the code correspond to 7 and 8. In 7 for binary, suppose this is the 7, this is 8. Okay, for 7 you are having the code in gray code, you are having 0 1 0 0. For 8, in binary you are having the representation like this. But here you are having 1 1 0 0. See here, only this bit is changing, remaining bits are same. So that is the advantage of gray code or unit distance code. Here we are arranging the code in such a way that only one bit position only will differ. Remaining bits will be unchanged. Is it clear? Sequential code and unit distance code are not same. This is the sequential code, binary code. Okay. Here you are getting the unit distance code. These two are not same. So here we have given one particular method how to convert a binary number into gray code. Okay. Later we'll convert the gray code into binary. For that you require some formula, but as per gate exam point of view, you no need to remember any formula. Okay. See here I have converted binary to gray. Okay. Later I have to convert gray to binary back. So for that I require some formula. So that's why I will give one more approach. First I will give the formula and then I will give the architecture. Okay. How to convert binary number or binary code to gray code. And then with the help of those equations I will get back the binary code from the gray code. Okay. Right. So here if you observe, for 4-bit case we have considered, I am assuming 4 bits as like B3, B2, B1, B0. 4-bit binary code as B3, B2, B1, B0. Here B3 is the MSB. Okay. Similarly 4-bit gray code I am assuming as G3, G2, G1, G0. Now I am having binary code, I want to convert into gray code. Like that. So here what we are doing, first step, whatever the MSB bit I am having, I am copying that bit as it is, right? So that means directly what we can say, G3 is nothing but B3. See, while converting from binary code to gray code, whatever the MSB bit is there, that one I have copied as it is. So I am writing G3 equal to B3. How I am writing next bits of gray code? By comparing two bits. If there is a change, output is 1. If there is no change, output is 0, right? Fine. So here I am giving one tabular form. I am considering 2 bits. So 2 bits if you are having 4 combinations you will get, right? Okay. Now what we have considered, whenever there is no change, output is 0. Whenever there is no change means what? Either input bit, those 2 bits are same. That means either both the bits are zeros or both the bits are 1. Yes or no? 2 combinations. If both are 0 or both are 1, there we have considered output as 0. Whenever there is no change, output is 0. Whenever there is a change, that means 0 to 1 or from 1 to 0, output we have considered as 1. What is this truth table? Yeah, XOR, right. A XOR B, Y equal to A XOR. So here we have considered 2 bits. Say for example B3, B2 if I consider, here I am getting exclusive OR operation. So here I can write G2 equal to B3 XOR B2. I am comparing these 2 bits, I am getting G2 bit. So G2 equal to B3 XOR B2. Similarly you can write G1 equal to B2 XOR B1. B2 XOR B1. And then G0 equal to B1 XOR B0. B1 XOR B0. You don't need to remember any formula. Just I wanted to convert later gray code to binary code. For that I require formula. So that's why I am giving this another method. Okay. See here we are having the binary code. That means what? B3, B2, B1, B0. This is the binary code available. Now what we are doing, whatever the bit B3 is there, that bit we are copying as it is, right? So B3 I am copying as it is. That is nothing but your G3. Next, B3 XOR B2. That means I am doing exclusive OR operation on these 2 bits, and then whatever the bit I am getting, that is nothing but G2. Next, B2 XOR B1, and then B1 XOR B0. So this is the binary code. So whatever the method earlier I have given, binary to gray code. Okay, copy MSB bit as it is and then check 2 bits. If there is a change, output is 1. If there is no change, output is 0. Okay, you can follow that method or you can remember this architecture. See here what we are doing, MSB bit we are copying and then we are doing exclusive OR operation on successive bits. B3 XOR B2, that output is G2. B2 XOR B1, G1. B1 XOR B0, G0. Binary to gray code conversion. You can remember this architecture or whatever the method I have given here. You can follow either of these two methods while converting binary code to gray code. See, here I have considered ABR like 2 bits. Okay, in this case you can assume say B3 B2, B3 B2 or B2 B1 B1 B0 like that. Here we are performing successive, we are checking 2 bits and we are writing the output. Okay, so that's why I have considered 2 bits. So in the place of these bits I have placed here. See, here AB I have assumed output is A XOR B. Here B3 B2 are the inputs, output is B3 XOR B2 like that. B2 XOR B1, B1 XOR B0. Next one is gray code to binary code. Here we have discussed how to convert binary code to gray code in 2 methods. First method and then this is the second method. You don't need to remember any formula. Okay. Now next one is gray code to binary code. Next one is gray code to binary code. Gray code to binary code. That means we are having the gray code. That means G3, G2, G1, G0 is available. We want to convert that gray code into binary code. That is B3, B2, B1, B0. If we are having the gray code, then how to convert that gray code into binary code? Now let us see. So here, if you observe, we are having the formula for gray code, right? From this, now let us get back our binary code. So here we are having G3. G3 is nothing but what? Your bit B3. So directly I can say B3 is nothing but G3. If I am having the bit value G3, so directly I will copy that bit. That bit is nothing but your binary MSB bit. Okay. Next, I wanted to get B2. I am having the code G2. See, here I am having G2 is available. From this I wanted to get B2. See, here in this particular expression I am having B2, but in addition to that I am having B3 also in exclusive OR with B2, right? So now I will try to eliminate this particular term so that what I will get B2 from G2. So here what I will do, I will do XOR on these two. Let us see whether we are getting B2 or not. Let us see. So B2 is nothing but B3 XOR G2. See here, very simple. Previously we are having the binary code and then we have converted into gray code. Now we are having the gray code. That means what? Suppose 4-bit case I am talking. G3, G2, G1, G0 is available. From that I want to get the corresponding binary code. Okay. Now G3 is nothing but B3. That's why I have directly written your MSB bit of binary code is same as G3. Next, B2 I wanted to get, but I am having the code G2 as what? B3 XOR B2. Here B2 is present, but in addition to that you are having B3. Now let us see. I am performing B3 XOR G2. Substitute G2 value here. B3 XOR G2 is nothing but B3 XOR B2. See, here we are having exclusive OR operator on 3 variables. Okay. So that means here we can apply associative law. Okay. Exclusive OR operator will satisfy associative law. Regarding this, I will mention in the second chapter. Okay. We will come to know exclusive OR operator will satisfy associative law. For the time being, you assume it is. Okay. It will valid for exclusive OR operator. That means XOR operator will satisfy associative law. For the time being, you assume that one. That means whenever you are having 3 variables, okay, 3 variables or more, okay, when you are performing the same operator among the variables, you can change the order of the variables, right? So that means here you are supposed to perform XOR on these 2 first and then with this one, right? So I can perform XOR on these 2 first and then with this one. XOR operator will satisfy associative law. Regarding this, I will mention in the second chapter. So here what you will get? B3 XOR B3 and then XOR B2. B3 XOR B3 and then XOR B2. Okay. So now let us see. Here B3, B3 both are same. Now let us observe here 2-bit case. If both are both are same. Here B3 you are having, here B3. That means here both the bits are 0 or both the bits are 1. Output is what? 0. Yes or no? If both the bits are same, output is 0. B3 XOR B3. So I am writing here 0 exclusive OR B2. 0 XOR B2. That means what? here I am having two variables. One of the variable is 0, other variable is b2. For the time being, see here I am considering a is 0. See here you are having two variables, a, another one is b2. Okay, here I have considered a and b are the variables. A is 0. Okay, when a is 0, just observe the output with respect to other input. Here if b is 0, output is 0. If b is 1, output is 1. That means what? If you are having a is 0, output is nothing but the other input b. Other input b, right? So that means 0 XOR b2 is nothing but b2. So I am getting b2 only. So I have given this explanation whether I am getting b2 or not. Okay, so that means what? See here b3 is nothing but g3. So if you are having the code g3, then I will copy that bit as this. That is nothing but my MSB of binary code. Then in order to get b2, I will perform XOR on these two. Similarly, in order to get b1, I will do XOR on these two. Similarly, in order to get b0, I will do XOR on these two. Okay, so directly you can write b1 equal to do exclusive OR on these two. That means b2 XOR g1. Next, b0 equal to do XOR on these two. b1 XOR g0. This explanation I have given whether I am getting b2 or not. Okay, directly you will get like this. See here b3 is nothing but g3. b2 is nothing but do XOR on these two, that is b3 XOR g2. b1 is nothing but b2 XOR g1. b0 is nothing but b1 XOR g0. You don't need to remember any formula for GATE exam point of view. Here I am giving the complete explanation just in order to get the complete idea how I am getting binary code from gray code. Okay, so that's why previously I have given how I am getting from binary to gray with the help of formula. I am using the same formula in order to get the binary code from the gray code. Okay, now with this 4 formula, now I will give the architecture. You remember that architecture. So here gray code is available, that is G3, G2, G1, G0. This gray code is available. Now we have to convert this gray code into binary. So first I am copying MSB bit as this. That is nothing but what? Your B3. Okay, now B2, how am I getting? B3 XOR G2. That means do XOR on these two. B3 XOR G2. So the resultant value is B2. Next, B2 XOR G1 is nothing but B1. B2 XOR G1. That is nothing but B1. Next, B1 XOR G0. B1 XOR G0. That is nothing but your B0. Just remember these two architectures. Architectures are sufficient. See, while converting from binary to gray, here or from gray to binary. In both the cases, what we are doing, we are copying MSB bit as it is. In both the cases, either from binary to gray or from gray to binary. Whereas in binary to gray, we are performing successive approximation on two. We are performing exclusive OR operation on successive 2 bits. Okay. On successive bits, we are performing exclusive OR operation. We are getting the corresponding gray code bits. Whereas in gray to binary, we are performing XOR diagonally and we are getting the corresponding binary bits. Is it clear? Just remember these two architectures. While converting from binary to gray or from gray to binary, we will copy MSB bit as it is. While from binary to gray code, on successive bits, we will perform XOR and we will get the corresponding gray code bits. Whereas from gray to binary, we will perform XOR diagonally and we will get the corresponding binary bits. Okay, so just use this particular architecture. Use this architecture. I have given earlier binary to gray, one tabular form, right? You try to check each one for 2 combinations. Assume, see, whatever second column you are having, that is the gray code, right? Put the gray code here, use this particular architecture, whether you are getting the corresponding binary or not. See, already you are having the tabular form, binary code and gray code. Now, each one of you can verify for 2 cases. Whatever you are having the second column, in that column you can consider the gray code, any of the available. Okay, whether you are getting the corresponding binary or not, just check. Each one of you can try for 2 combinations. You are already having the gray code, just use this architecture, whether you are getting the corresponding binary or not, just verify. Yeah, gray codes you can use whatever the earlier I have given one particular example where you are having multiple number of bits. Okay, if you are representing the binary code, okay, then if there is the ambiguity while converting, see, all the bits if it is supposed to complement, right? Wherever there is the ambiguity, there we will use the gray code. So that what will happen? whenever you are having two successive codes, only one bit position only will change. That is the advantage of gray code. So if you are having, suppose some devices or machines will be there where there will be rotation, right? Circularly rotating will take place, right? So there, if you are supposed to find out the angular position of the shaft, there you can use this particular gray code. Instead of that, if you are using say binary code, what will happen? Because of some bits, right? If all the bits may not change, right? Then you will get some other code. Or otherwise, just since it is a rotational operation, okay, since it is a continuous process, there if you are representing with the respect to binary code, there you may get some ambiguity if you are using binary code, because that position of the shaft is exactly you have to represent the corresponding gray code. The advantage of gray code is because see, whatever suppose you are having suppose 12 segments or any 8 segments or whatever, if you are representing each segment with the binary code, then there will be ambiguity in order to know the position of the shaft. There you can use the gray code, so that what will happen, the successive codes, if you are considering any two segments, only one bit position only will change. That is the one real-time application of gray code, and we will use this gray code in K-maps also while doing the simplification. There we will place the min terms in such a way that adjacent min terms are differed by only one bit, like that.